Chapter 1, Section 1. And this is what we use math in the real world for. In fact, there are people that get paid lots of money to do this, hired by insurance companies and stuff and businesses. So the next thing that we want to do for example number 5 is we're going to fit curves to data. So we showed in example number 2 that the percentage of females in the U.S. prison population has been steadily growing over the years. Model this growth graphically by using a graphical model and then suggest an algebraic model. So what we're going to do is we have these two values. This is the time in years, and this is the percentage of the total population. In other words, when they first started this data collection, the 3.8% of the prison population was female, and then 20 years later, 6.7%. So it doubled over 20 years. And so what we're going to do is we're just going to enter that into our handy dandy calculator. So I'm going to come in here. I'm going to clear a bunch of stuff out from our previous problem. If I hit stat, now another thing you could do is you could hit clear list and then choose L1 and then hit comma and then choose L2. Now what I just did is I told my calculator to clear the list L1 and L2, but I keep getting a syntax error. I don't know why. There's something goofy with my calculator, so I'll just have to do it manually. Oh, it worked. I don't know. I got to figure out what's wrong with that. So now I'm going to enter in 0 for my first term, 5, 10, 15, and 20. Now, based on what I told you guys on the last problem, what is time? We have time versus percentage of female population. Is time independent or dependent? Independent. It's easier to think of what depends on what. So over time, the female population is increasing, right? Time is increasing naturally, right? Whoa. All right, here we go. 3.8, 4.4. So what we're saying is that the female population increases over time. So therefore the female population percentage is dependent upon time. And so if the female percentage of population or population percentage is dependent upon time, then time is the independent variable. So let's look at the graph. So we've got the stat plot on. I'm going to go to zoom. What was that I told you guys to look up? Zoom what? Zoom stat. Thank you. So glad you're here. I almost forgot that. All right, there it is. Boy, that doesn't look like much of anything. What do you guys think? Well, it kind of looks like a straight line, right? Clearly there's some numbers that aren't, like, it's not perfectly straight. So I want to do something. So let's do a linear regression on this, but before we do that, there's a thing that we call diagnostics. And so it could be turned on your calculator, it may be turned off. So what you would do is you would hit second, catalog, and instead of scrolling through all these letters to find the different programs on my calculator, if you look really close, there are letters. If you just hit, like this letter, I think is D, it'll take you right to the D's. And so what I'm going to do is I'm going to scroll down to diagnostics on, turn that on, it's on. Now whenever I do a linear regression, it'll give me an R-squared value. Now the R-squared value is kind of a way of letting me know how close every data point is to the line. So why would I want to do that? Well, let's see. Let's go back to the graph. Now what I'm going to do is I'm going to select stat, go to the calculate menu. It looks like a straight line, so I'm going to try a linear regression. By default, it'll do L1, L2. I want to store this in Y1, so I have to hit the vars button, select Y vars, and then choose 1 for function, and I want to store that in Y sub 1. Hit enter. Now my R squared value, that's a pretty high correlation. It's 0.98. It's kind of like a percentage. It's not exactly a percentage, but it's like saying 98% of the points are on the line. It's kind of that way, but that's not really what it is. It's really a measurement of distance from the line. And the closer this is to 1, the better. Okay? Alright, so let's look at that graph. Now here's the thing, because it's such a small amount of space, maybe it is a quadratic. Maybe it's something else. So let's try just to see which one it is. So now if I go to the calculate menu and I do a quadratic regression, and again I'm going to select y-vars. Oops, I didn't want that. Function, and I've already got one equation stored in y1, so now I'm going to store this in y2. Now I hit enter, and notice that my R square valued, isn't that pretty darn close to the same? The other one was 0.98, this one's 0.98. So do you think either one could be an accurate predictor? Could be, could be. So what I'm going to do is now I'm going to look at the graph. Not much of a difference, is there? Not much of a difference at all. Well, the textbook says to use a linear fit. So if I were to use a linear fit, what would we label that as? Well, let's look and see. The linear fit would be 0.146x plus 3/8. My quadratic fit would be a lot of numbers. So just for operation's sake, just for doing your math, which one would you choose? The first one. It's easier, right? Mathematicians do this all the time, especially when they're programming computers. The second one takes a lot more work for a computer to do than the first one. And by looking at the graph, you could see there really isn't that much difference, is there?